for 1.3, example number 3, we have a table of the U.S. population, and that table looks sort of like this. So we have the year, we have the population in millions, and then we have a ratio. Okay, and so we're going from 1998 to 2003. I should mention that the population is written in millions, so it's pretty big. So, for example, the population of the U.S. was 276.1 million, then it was 279.3 million, and then so on and so forth, 282.4 million, 285.3 million. You guys double check, make sure I don't make a mistake. 288.2 million, 291 million. And so what we want to do is we want to check the ratio to kind of compare the growth from year to year. So the easiest way to do that is to take the second number, in this particular case 279.3, and then divide it by the 276.1, and that yields 1.01 roughly. And if we do that with the next two numbers, 282.4 all over 7, or 279.3, we'll get about 1.01. And again, if I say 285.3 all over 282.4, again we're going to get a 1.01, and so on and so forth. So if we were to continue down that road, you see a ratio of about 1.1. Now what that means is that's a good way that if you do that and you compare the ratios and you see that pattern of 1.1, 1.1.1, that's probably an exponential function, or we can model it as an exponential function. And so in example number 3, this is real live data. If I want to create a mathematical model or function, I would look at this data and I would say, oh, this is probably exponential. I probably have a base of 1.1. That's how you could tell that. So then how do I, the question really wants to know is how many people, that's supposed to be the word how many people or population, right, in 2010. Well, if I think that my base is 1.01, I'm going to raise that to a power, but I also need to have the initial condition. So my initial condition is going to be 276.1. And so let me break this down in like regular English, informal language. To get from 276.1 to 279.3, I'm multiplying by 1.1. Then whatever that number is, I multiply by 1.1 again. Then I multiply by 1.1 again. So I just need to figure out how many times I'm going to multiply this whole thing by 1.1. Well, 2010 is actually 12 years from 1998. So I'm going to multiply this 12 times. Okay?
What?
Well, you could think of it this way. This is like, if this was t for time, this would be 0, this would be 1, 2, 3, 4, 5, and if you keep going.
I get that, but why do you put it to the 12th power instead of just timesing it by 12?
By what?
Instead of just timesing like the thing by 12, why do you put it to the 12th power?
Well, because remember, we're going to multiply by 1.1, and whatever that number is, we're going to multiply by 1.1. and we're going to multiply by 1.1 12 times. So what's the shortcut way to write we're going to multiply by 1.01 12 times?
Oh, okay.
1.01 raised to the 12th power.
Okay.
Does that make sense?
Mm-hmm.
Now if you plug that in the calculator, let's take a look in this fancy schmancy calculator here. Let's zoom in too. So I'm going to say 276.1 times, and I'm going to put this in parentheses, 1.01 raised to the 12, and then hit enter. And so it's about 301.1 million, or whatever the number says. 311.1. I was like trying to approximate it. It's hard to do calculus. It's early in the morning. I just had my coffee. Anyways, that's the answer in the book. I just can't talk. So that's our answer. So this is what we do this all the time. So growth in general, especially in population growth is usually an exponential function in most cases. And so if we can find this ratio as to how much it grows from year to year, we can usually write a mathematical model. So now we're in 2014. I suppose we could look up and see what the current population is. We won't do that now, but if you're curious, look it up, Google it later, and we should be close to that. Okay? All right.